Hello, my name is Anish Sankaratri, and this is my interesting mathematics project on the birthday paradox. I chose this topic because me and a friend share the same birthday, and I was curious to what sample size is needed for two people to have a high probability of sharing the same birthday. Some history on this topic is that this was first proposed in 1939 by Richard von Mises. The birthday paradox remains one of the most fundamental theorems in probability, as it states a lot of which is in our modern day statistics. Mises proposed that in a group of 20 or more people, there is a high chance that two people share the same birthday. Now, this theorem was not fully developed at the time at which Mises proposed it. It was but very close to the actual number. Later, in 1957, the theorem was further developed on by American science writer Martin Gardner in his Mathematical Games column in the Scientific American magazine. Gardner just refined Mises' theorem. Instead of saying high probability, he said 50% or more. So, for this theorem to work, there are three assumptions that need to be made. You must assume that the year has 365 days, so leap years and other unforeseen circumstances are ignored. Birthdays are independent between people, so there is no outside factor influencing anything. And then all 365 possible birthdays in a year are equally likely, to avoid that one day has more than another day. So if you notice this equation here, you have 365 factorial. This is the amount of days in a year, the chances in a year. And then you have 365 to k. K in this equation is your sample set. So if I wanted to find the sample set of 43 people, I would plug in 43 as k. So when you plug in everything into your equation, you should get a decimal answer, and then you multiply that by 100, and that will be your percentage. So if you notice on my graph here, as the sample set grows on the bottom, so do the chances of having the similar birthday. So if you notice at 5, it's pretty low, and then if you keep going up and up and up, it reaches 50% at around 23 people. And then if you keep going up, it peaks out at 100 at around 56 or 57 people. So this is a visual representation of what this looks like. As I've entered my birthday in here, and then I've also entered just a random example birthday. So this will run one trial of 23 people, and we will see how many successes there are. So in this trial, as you can see, 23 people about enter, and we already see that there is already 2 matches just within these 23 people. But remember, you have to keep in mind this is only one trial. This isn't the bigger equation. Now we're going to run 20 trials, and we will see how many successes and how many failures there are, and then the rate of success in each trial. So as you can see, we've already started off with 2 successes and 1 failure, and it had a sudden drop, but it's climbing back, but it's also dropping, climbing back. This is the statistics of this theorem. It's not a definite number, it's just the amount of trials you have to run. So let's run 1,000 trials and see how that plays out. As you can see, in 1,000 trials, the number stays very close to 50, and so do the successes and failures. And then in this trial, we're going to explain the comparisons between. So if you notice, just between 2 people here, you can see that there's only one comparison made. Therefore, there is a very low probability that these people share the same birthday. Now let's increase our sample set to 4 people. So if you notice, in 4 people, each person has to ask the other 3 people. Therefore, it increases our number of comparisons and increases our probability. So let's increase our set to 6 people. And in this set of 6 people, you notice that this person has to ask the other 5 people, and each person has to ask the other 5 people, therefore increasing our number of comparisons and increasing our probability. So let's go to 10 people and see how that plays out. So in 10 people, if you notice, there's so many comparisons being made because there is a larger number of people. So 45 comparisons are made in a set of 10 people, and look at our probability. It has skyrocketed to 11.7%. So at 23 people, this is where our desired 50.7 is. So all in all, this topic is very nice to know, and it lays down one of the foundations for statistics. So I hope you enjoyed my presentation. Thank you.